Alright guys, we're broadcasting from Avery's hospital room actually right now. Say hi Avery.
Um,
Uh,
should I rip my paper off now?
I don't know, she's making a snail thing
I'll
right
do
now.
it.
Oh, so she's going to be ripping some paper here for a second.
Sorry for a second.
Alright, while she's doing that, it's time for your visible quiz. So you have these letters A, B, C, or D. So fill them in, something like this. You can make them all the same letter if you want, but you just do your best. Pause the video now, and then when you're done with those 10 questions, unpause it. Alright, so the answers to your invisible quiz, if you haven't actually filled them in yet, pause it and fill them in, are... the answers to your invisible quiz are D, C, A, D, B, B, A, B, A. So score yourself really fast. And again, they are D, C, A, D, B, that's B, B, A, B, A. So, see what your score is. What do you think the expected score should be? So if we look down here, find your score, and we have 10 questions. And out of those 10 questions, you have 4 choices for each of them, right? So what do you think you should have scored on there? 100%? I mean, if you're really, really lucky, it should be 100%, right? So, I mean, out of 10, and you have a 1 in 4 chance of getting each of these right. So what do you think you do to figure this out? So let's think if there was only a 50-50, like a coin flip. You flip a coin 10 times, and half the times are going to be heads, half the times are going to be tails, and you're just guessing. Should be right half the time, right? So it should be right 5, should be the expected score. So in this case, you take 10 times 1/4, and a quarter of 10 is unfortunately not a nice number, it's 2.5. So that's how many you should expect to get. So how did you do? Did you do better than expected? What do you think the probability that you're going to get none correct is? So how in the world do you figure that out? So if X is the count of correct answers, what's the probability you get 0 correct? Well, that means you get them all wrong, right? So that means we have a 3 out of 4 chance of getting each one wrong, and that needs to happen 10 times, right? Alright, I'm going to answer the phone. Alright, so this needs to happen 10 times. So the first one has to be wrong, second one has to be wrong, all of them have to be wrong. So we have 3/4 to the 10. 10 right in a row, that's what you're going to have. 10 wrong in a row, that's what you have to have. This probability, so whatever 3/4 to the 10th is, that's that probability. It's probably get them all right. Well, that means you get the first one right, which would be a 1 out of 4 chance. You get the next one right, which is a 1 out of 4 chance. And that needs to happen 10 times. What's the probability that you have 4? So here's the problem with that. You can get like the first 4 right, and then all the rest no. I don't really want to write all these out. Or it could be the first 3 are yes, and the 5th or 6th one's a no. Or is a yes. Or the last 4 could be yes. So I mean, I can figure out the probability of this particularly happening, where I have 4 yeses, the first 4 are yeses, and the other 6 are no's, and I still have to have 4 yes, and then 6 no's. But the tricky part is, that's not the only way it could happen. And what do I have to do with all of them is I basically have to add up all these different probabilities. So the probability of this combination versus, let's say I switch the yes and the no. That's a different order in which these things are happening. That's you getting the 4th one wrong and the 5th one right. That's different than getting the first 4 correct, especially on a test. So that's the part that's tricky about this, and that's the part that's making this a binomial question versus just the basic probabilities that we've been dealing with so far. So everything up until this number 4 problem, it's really just basic probabilities. But now, once we have this, we have to figure out how to deal with the binomial setting. So what do you need for it to be considered binomial, which is based on our notes today. Alright, so the big thing about binomial is the bipart binomial means 2, right? So in this case, when we're talking about binomial setting, which is also known as a Bernoulli trial, because he is the person that basically defined this for the first time, is you have 2 outcomes. And I know that sounds like it's limiting, but for the most part, think of it as success versus failure. In the problems up above, the blank quiz, you think 4 outcomes, but there really are only 2. Either you get the problem right or you get it wrong. It doesn't matter that there are 4, A, B, C, or D. Same thing with like rolling dice. So you could talk about rolling a 5. Well, there's a lot of different numbers you could roll, but you either roll a 5 or you don't roll a 5. So you have 2 outcomes. You also have a fixed number of trials. Which is generally going to be denoted by n. So n equals some sort of a number. And our outcomes are successes or failures, fixed number of trials, n. So another problem before n was 10. The probability of success is the same. Each trial. And it's usually denoted as p. The probability of failure, so I'm going to say the same thing, but for failure, is also the same. A lot of times that's denoted as q, which is 1 minus the probability of success, or vice versa. So some people will use p and q, I tend to, and some people just use p and 1 minus p. And then the last one is each trial is independent. If you don't have each independent one, you can't multiply them together like we're looking at in the past. And these 2 really go together for a lot. Alright, so pause this and make sure you take down your notes before you move on. Alright, one thing before we move on here to the next question is, what do you have to tell the AP if you're looking at an FRQ? Well, one thing you have to tell them is you know that it's binomial. That's a terrible B. And you also have to tell them what the number of trials is, so in this case n is 6, and what the probability of success is, which would be 1/2. Very similar to when it's normal. You have to tell them the mean, and you also have to tell them the standard deviation. And that notation is always n, mean, comma, standard deviation. We don't use that too often, but they use it sometimes, and you've seen it in some of the notes in the homework. So in this case, the notation would be b for binomial or Bernoulli, n, in this case 6, and p, which is 1/2. So that's the main thing you have to tell them, is you are recognizing it's a binomial situation. You don't have to prove it. I mean, we're proving it using these 4 points, but the second you realize that this is all true, you tell them you're realizing it is, you tell them what the number of trials is, and you tell them what the probability of success is. Alright. There are a couple things I want to just highlight, and they are highlighted, like actually in your notes, is a discrete probability. You have the probability that the number of successes is like 3. And it's not a continuous. You have 3 successes or 4 successes. You can't have 3.2 successes. It doesn't make any sense. And you always have to define this x. So it's a count. And it's a count of successes. And the parameters, which we just talked about, was n and p. And here's that notation again that I was just talking about. Called Bernoulli trial. Possible values of x are any whole numbers from 0 to n. You can have 0 successes. That's perfectly fine. When you think back to your quiz there, you could have any value from 0 to n, which actually makes it seem like there's too many trials. Because if it's from 0 to 10, that's actually 11 options, but you can only win up to 10 different things. Alright, so what I want you to do is take a couple minutes and go through the next problem. And it's talking about blood types. Blood type is inherited. Both parents carry genes for O and 8 blood types. Each child has a probability of 0.25 of getting 2 O genes and having blood type O. Different children inherit independently of each other. Number of O blood types among 5 children in these parents is the count of successes. Alright, so why don't you take a second and decide whether this is a binomial setting, and if so, why or why not. Try that for both 4 and 5. And then when you're done with both of those, unpause it and we'll go through the answers. Alright, so this is a binomial setting, and we have binomial. The number of children is 5, so that's our count. 5 successes or failures. And the probability of success would be 0.25. Alright, so for dealing cards, what do we think? I'm hoping we said no, because deal 10 cards from a shuffled deck, so it just says deal them out. Do they replace them? If they replace them, then each set would be independent, and so no, because it's not independent. So that was our last one. It also fails number 3, because the probability is going to change every single time as you're taking cards out of the deck. Alright, flip over the page to number 6 next. So, suppose that 25% of all quarters in circulation are state quarters. If an SRS of 5 quarters is drawn, what's the probability that exactly 2 are state quarters? Is this a probability question in the binomial setting? Alright, so I want you to take a couple minutes, so pause this in a second, and then try to answer these next 2 questions. And once you get a couple minutes to try them out, then unpause them and see if we agree. Alright, so I'm hoping you're thinking that this first one is binomial, which it is, and it's binomial. N would be 5, and P would be 0.25. So number 7 wasn't really a question, it just talked about one of the answers. But the tricky part about number 7 is there is more than one way of doing this, which I'm hoping you're realizing. So they're showing us that it could be the first one is a state quarter, and the next 2 are regular quarters, and then we get this outcome. Now the tricky part is what is another way the 2 could occur? Well, it could be state, state, and then regular quarter, regular quarter, regular quarter. So what's the probability of obtaining this outcome in this order? Well, the 2 states are again 0.25. We have 2 of them, and then we have to have our 3 quarters, which would be 0.75 to the third. But the big thing to notice is these are the same thing. So in fact, the probability of 2 state quarters and 3 regular quarters in any order is, well, the same thing we just found twice. 0.25 squared, so we have 2 state quarters, and 3 regular quarters is 0.75 to the third.